Okay, let's talk a little bit about gas density and molar mass. Density and molar mass of an ideal gas can be found by rearranging the ideal gas equation. So if we do a little creative substitution and say, well, moles is mass divided by molar mass, then PV equals nRT becomes PV equals mass times RT divided by that little script be looking M, and that M we're using as a variable for molar mass. Solving for molar mass, we get molar mass is equal to MRT divided by PV. If we want density, then we can do a creative substitution again and say mass divided by volume is equal to density. So molar mass is equal to density times RT divided by P. Or solving for density, density is equal to pressure times molar mass divided by RT. So if we look at an example, student collects a sample of a gas in a 0.220 liter gas bulb until its pressure is 0.757 atm at a temperature of 25 degrees Celsius or 298 Kelvin, since we've done that a couple of times. If the sample had a mass of 0.299 grams, what's the molar mass of the gas? So if we look at this problem, I transferred the data from the problem text, and here's our formula. Molar mass is equal to MRT divided by PV. Just a little plug and chug once you have the formula, 0.299 grams, 0.0821 liters atm, mole, and Kelvin, and then 298 kelvins. Then we're going to divide all of that through by our P, 0.757 atm, and our volume of 0.220 liters. Liters are going to cancel, ATMs cancel, kelvins cancel, and we're left with grams divided by moles. So our molar mass is going to give us 43.9 grams per mole. Now that definitively won't tell you which gas it is, but it could certainly limit our list of suspects. Carbon dioxide is pretty close, propane's pretty close. So if you had a couple of gases to pick from, you could get which gas it was. If it was flammable, we'd say it's propane. If it's non-flammable, we'd say it was CO2 if I gave you an either or. But you can limit your list of suspects and say, which gas might this be? You could certainly eliminate some based on the molar mass calculation, but it's not going to definitively tell you unless I just give you a very limited list of choices. Next, we want to calculate the density of argon gas at 25 degrees Celsius at a pressure of 760 millimeters of mercury. So room temperature, normal barometric pressure, what's the density of argon gas? You can compare that to the mass of other gases and tell whether they would sink or rise. Molar mass of air is said to be about 29 grams per mole. So anything heavier than that is going to tend to sink in low-lying areas. Anything lighter than that is going to tend to rise. So doing our density calculation, we got 298 Kelvin, molar mass of argon from the periodic chart is 39.95 grams per mole. 760 millimeters of mercury is 1 atm, so we're just going to work with the 1 atm. So we're going to plug and chug 39.95 grams per mole. Pressure 1 atm. Our R is the universal gas constant, 0.0821 liters atm, moles, and Kelvin. And our temperature is 298 Kelvin. We're going to cancel all of our units out. ATMs are going to cancel, moles are going to cancel, Kelvin's going to cancel, and the density of the argon is 1.63 grams per liter. Notice that it's grams per liter, not grams per milliliter. One, it gives us a more manageable number, but two, gases are pretty low density, and so using a larger volume unit actually works in this case. Milliliters would give us too small of a number.